Assalamualaikum and greetings. My name is Muhammad Alif Najmi bin Muhammad Hushaini from course code AS245 Science Applied Chemistry, and today I want to present about my final year project, which is synthesis of high surface area gold electrode by electrodeposition using the alloying process for the subject FSG 671 final year research project. Nanostructured gold electrodes created by dealloying gold has gained significant attention in the field of analytical chemistry. This conductive material has an open, 3D porous framework made up of nano-sized pores and ligaments with surface areas that are tens to hundreds of times larger than planar gold of an equivalent geometric area. The high surface area coupled with an open pore network makes nanoporous gold an ideal support for the development of chemical sensors. Nanostructured gold electrodes are reviewed specifically as they are related to the development of immunosensors, enzyme-based biosensors, DNA sensors, Raman sensors, and small molecule sensors. By the combination of electrodeposition and dealloying, sponge-like nanoporous thin films and coral reef-like nanostructures can be obtained. When compared to other techniques that require templates, templateless nanostructure formation is advantageous because the solution process allows us to deposit materials on original micro or nano pattern even though they are formed on 3D structures. In general, alloy electrodeposition necessitates a complex solution containing ion, complexes, and additional ligands for adjusting deposition potentials to be close enough for co-deposition. For problem statement, the synthesis of porous electrodes on tiny current collectors by using the alloying process is critical for the successful application of microelectrochemical systems such as microsensors and microfuel cells. Furthermore, nanotechnology has grown in importance in the study of fibrous materials, specifically nanofibers and silicate nanocomposites, where the synthesis, characterization, and unique properties have been studied. In recent years, there has been a great deal of interest in the electrochemical deposition of nanoporous gold on a solid substrate. This simple technique boosts the electrochemical activity of the nanoporous film by allowing for fine control over the growth and nucleation mechanism which determine the morphology of the deposited film. The development of glucose sensors has piqued the interest of researchers due to their potential application in a variety of fields such as clinical diagnosis, food monitoring, fuel cell, and so on, because of low electrochemical performance for glucose detection. Several techniques including optical sensors, electrochemical sensors, and colorimetry were used to detect glucose. This study is significant because metal nanoparticles have piqued the interest of many scientists due to their unique electronic, optical, and catalytic properties. The incorporation of metal nanoparticles into thin films is especially important for a variety of applications, such as biological sensing and the fabrication of optoelectronic nanodevices. Although gold is a poor catalyst in bulk, nanometer-sized gold nanoparticles can exhibit excellent catalytic activity due to their high surface area-to-volume ratio and interface-dominated properties, which differ significantly from their bulk counterparts. Nanoporous gold also is a promising material for drug delivery applications and studying the influence of surface modification on drug release kinetics. The objective of study. The incorporation of metal nanoparticles into thin films is especially important for a variety of applications, such as biological sensing. The use of gold nanoparticle building blocks for the creation of electrochemical sensing device is also promising. The following are several objectives that want to be achieved within this study. The first one is to produce a high surface gold electrode by electrodeposition for electrochemical sensing. The second one is to characterize gold nanostructures. And last one is to provide electrochemical performance of nanostructured gold electrode for glucose detection. The most common method of preparing nanoporous gold is by dealloying. It is a top-down method in which a gold alloy containing other less noble metals is treated in a corrosive environment with or without the application of a potential by means of dealloying. The dealloying process selectively removes the less noble metals from the gold alloy, resulting in a nanoporous structure with interconnected ligaments. The shape and size of the alloy are important because the nanoporous gold formed after the alloying process keeps the alloy's shape and size. The nanoporous gold structure can be made as a supported thin film or as a freestanding structure. When compared to freestanding nanoporous gold, supported nanoporous gold is more physically stable and easy to handle, and it is most commonly prepared for use as a working electrode in electrochemical experiments. Using supported nanoporous gold, it is convenient to separate the interfacial boundary between nanoporous gold and clip holding electrode. The charge associated with the reduction of gold oxide, which is proportional to the real surface area of the electrode, is measured using cyclic voltammetry (CV) at slow scan rates. The roughness factor of an electrode can be calculated by dividing its real surface area by its geometric surface area. This method, unlike gas absorption measurements, can determine the surface area of thin nanoporous gold films. Quantitative analysis of glucose is essential in clinical chemistry. Glucose is typically analyzed using methods that use specific enzyme for glucose, ensuring that it is not easily disrupted by other sugars that may be present. The non-enzymatic and parametric glucose sensors is possible using nanoporous electrode or by modifying the dihydroporous electrode surface with other metals or metal oxides. Next, I will be presenting about result and discussion. The first one is deposition of gold. Cyclic voltammetry (CV) analysis was carried out for the deposition of gold on SPGE surface. The CV analysis was performed in egg to alloy solution containing 1 molar sulfuric acid by scanning potential from negative 0.3 volt to negative 0.8 volt and switch back to negative 0.3 volt at scan rate of 100 millivolt per second for one cycle as shown in figure beside. The forward scan shows the reduction of gold, inducing the deposition of gold particle onto SPGE surface. As shown on voltammogram, it can be seen that a small cathodic peak appeared at potential of negative 0.316 volt, demonstrating a little nucleation of gold particles on the SPGE surface. Thereafter, the current started to decrease from negative 0.318 volt to negative 0.602 volt due to the depletion of gold ions at the interface of the SPGE surface. Further scanning to the potential to more negative value at negative 0.6 volt resulted in a very small peak. Electrodeposition of gold on SPGE had a significant effect on the structure morphology, resulting in more complex nanostructure and larger surface area. The process was varied with different cycles, whereas electrodes were deposited with gold with 10 cycles, 30 cycles and 60 cycles using cyclic voltammetry. The application of various cycles for the electrodeposition affect the growth process, whereas larger amount of cycle resulted in larger structures in nearly compact gold layer. Now I want to talk about dealloying. Dealloying was done with two different methods, and the first one is dealloying through immersion method. The effect of cycles on the electrochemical behavior of 5 millimolar potassium ferrocyanide was also examined after the dealloying process have been done. Apparently, bare SPGE showed the lowest anodic and cathodic peak for potassium ferrocyanide as shown in figures that I have provided. However, upon the dealloying process of the SPGE, the redox current showed a step increase with a small decrease in the potential difference. The electrochemical performance of gold or SPGE is depicted in the figure that have been provided. The behavior of modified carbon electrodes was investigated by performing cyclic voltammetry in the range of negative 0.2 volt to 0.6 volt in 5 millimolar potassium ferrocyanide at 100 millivolt per second scan rates. It was found that bare SPGE give the least activity towards ferrous or ferric ions reaction since the electrode is least active compared to modified electrodes. Meanwhile, the presence of gold on the surface of electrode has increased the peak currents because of the properties of the gold ions to improve conductivity and surface area. The SPGEs deposited with gold have higher electrocatalytic performance for electrochemical reaction toward ferrocyanide ions than bare SPGE and can be attributed to the increase of active surface area of electrodes. The highest electrochemical reactions performance were shown by the SPGE deposited with gold by CV at 60 cycles. The electrode has the highest peak current. After we done with the alloying process, we will move forward for electrochemical characterization. The ECSA and roughness factor values of all gold nanostructures deposited on SPGE at number of cycles are shown in the table that has been provided. From the table, it shows that ECSA and roughness factor of gold nanostructures prepared with 60 cycles are found to much higher, with 8.115 cm² and 73.77 respectively. These values were the highest when compared to other gold coatings deposited at various cycle count. And the last part for result and discussion is the glucose detection. In order to assess sensor sensitivity, CV of various glucose concentrations in 0.1 molar sodium hydroxide were measured at a scan rate of 100 mV per second. As shown in the figure that I have provided, two distinct peaks corresponding to glucose oxidation appeared. The calibration curve was expressed as a dependence of the current value of this peak on the concentration of glucose, because the peak in the backward scan appeared more distinguishable. With the coefficient of determination R2 equals to 0.9884, the sensitivity was calculated to be 0.0106 mA over millimole cm², which present an excellent value. The standard deviation of the blank was also used to calculate the lower detection limit LOD. And the LOD for glucose in 0.1 molar sodium hydroxide was 2.484 millimolar, indicating that the nanostructured surface has strong electroactivity towards glucose oxidation, even at low potentials. And now we will proceed with the conclusion. And as for the conclusion, electrodeposition was used to create high surface area gold electrodes. Cyclic voltammetry analysis revealed that the electrode had improved electrocatalytic performance. The properties of gold have improved the electrode's conductivity and surface area. SPGE deposited with gold over 60 cycles and dealloyed by anodization has the best electrochemical performance and the largest electrochemical surface area at 8.115 cm². The electrode was then tested for sensitive detection of glucose in alkaline media, and it was successful, as the electrode detects glucose in various concentrations in 0.1 molar of sodium hydroxide with a sensitivity of 0.0106 mA over millimolar cm², and a lower detection limit of 2.44 millimolar, indicating that the nanostructured surface has strong electroactivity towards glucose oxidation, even at low potentials.